Hi, I'm Devendra Kapadia. I work at Wolfram. I'm the manager for Calculus and Algebra. And this afternoon, I'll speak with Itai Seggev at 5 p.m. about streamlining mathematics for education and talk about linear algebra initiatives that we'll take during the next year.
I'm Itai Seggev. I'm a senior kernel developer. I'll be presenting some stuff with my colleague Devendra here. Um, by itself, each one of these things is sort of small and not super impressive, but actually I became increasingly convinced as I prepared this talk, and so I hope you will also be convinced that together that they make a nice collection of enhancements. So I'm going to be talking about the various enhancements we've made to just make Mathematica a little bit more friendly, particularly for students, but also for anybody who uses it. And there will be sort of three areas, sort of dedicated functions for certain tasks, enhanced presentation of existing results, and improved documentation. So I'm going to start with enhanced presentation. So here's a nice cubic equation you might want to solve. And I'm using a trick here to solve it in 11.3. And it thinks deep thoughts, and it returns root of blah, which first of all is not very informative. And even if it were, I can read that. I'm like, oh, it gave me the polynomial back as a pure function, and it says it has 5 roots. Yay, because I didn't know the fundamental theorem of algebra. So now if you do this in version 12, you'll see something like that. Well, that looks much nicer. So we have one root that is about minus 1.83, and if I hover over it, it's a little hard to see on that screen, but if I hover over it, then there's a tooltip with the old input form if you want to know those details. Then we have a conjugate pair and a second conjugate pair, which we had to have pairs since all real coefficients. Now these look very different, but they're in fact the exact same expression. If I take the old result and stick it in the new kernel, then I see something that looks like the new result here. Conversely, if I take this new looking result and stick it into an old kernel, it evaluates to what it gave. So this is purely a change in formatting, not a change in what's actually returned. It's what we in the biz call typesetting. So some more examples. Here's solving something with fractional powers, and you get a power of a root object. Now, again, you get the same root object, the newly formatted root object raised to the 6th power. You could, when you were solving transcendental equations, you could get really scary looking things like this root object here with 20 or 40, however many digit numbers in it. Now, again, it's the same result, but you see something that's actually somewhat informative. You hover over it, you can see all the gory details if you want to. And here we have returning a conditional expression. Oh, did this guy lose? Are these out of order? Oh, they're just out of order. Right, so here we have a root inside of a conditional expression because we're solving trig equation, so we have a plus 2 pi I, and there's our new root object, as opposed to trying to figure out what we're looking at here. It's very clear here because it's so compact what we're looking at. Okay, couple details. The new formatting is not used when there are symbolic parameters because, well, there isn't a number we can stick in the little blob, so that will require further option. The new roots will evaluate, so if you save a notebook and send it to somebody running 11.3, it will evaluate correctly. Those roots will continue to work. However, they will not look very pretty. So if it's important for you for them to look something that doesn't look like it's a damaged notebook, then there's the system option right here. You can temporarily turn off the new format, or permanently, if you hate it for some reason, turn off the new formatting and use the old formatting. So that's root. Another guy which got Some enhanced presentation is C. So C is our undetermined constant that comes up in DSolve and other places. And so we have C of 1, C of 2, and so forth. Well, now it looks like something a little bit more familiar. They're subscripts rather than function application. Again, it's still the same expression. It just is formatted differently. And the most important differential equation, because basically every physical system is just this equation in disguise. That was a joke for the physicists out there. Again, we get now pretty formatting, C1 cosine of x, C2 sine of x. The traditional form is unchanged. Already we use subscripts. So this half of the slide is just change in presentation. But we now have C in lots of new places. So for example, by popular demand, we have it in integrate. So if you want the plus C, say generated parameters goes to C, and voila, you get a plus C. Sometimes constants aren't so constant. So in this example, we're integrating first with respect to x and second with respect to y. And I just said that backwards, but you know what I mean. And we get C1 of y and C2 of x, because if you take the mixed partial xy, then this term will fall out and that term will fall out. In addition, we have this in discrete integrals, also known as sums, and also in products. They work very much the same way. If you want more details on things and similar things, go to the What's New in Calculus and Algebra talk, which is tomorrow morning at 10:30. Okay. So switching to sort of dedicated functions, we have a bunch of new number domains in 12. Basically, we have signed versions of the reals, rationals, and integers. There are different standards for how to format these things. We picked the one which is very unambiguous. So the positive reals is r greater than 0. The non-negative reals is r greater than or equal to 0. Then there's no question about is the plus strict or not strict. It's just very, very clear. So these very much behave like you might expect. So if you ask if pi is a member of any of these domains, well, it's a positive real, it's a non-negative real, but it's not a negative real, nor is it any kind of rational number. Similarly, minus 1/2 is a negative rational and even a non-positive rational, but it's not an integer. And 0, as you might expect, is in the non-versions, but not in the strict versions. And you can use this in lots of places. For example, simplification. So is e to the x a positive real when x is an element of the reals? Yes, it is. And if x is if x is in the negative reals, is e to the x between 0 and 1? And again, that's true. And here's one with integers. So I'm asking, is abs of n equal to floor of n? And if n is a positive integer, that is true. If n is a negative integer, then that's false. Okay, so now, yeah.
Is there a way to type those in?
Yes, thank you for asking me, Brett. We have keyboard shortcuts for all of these. They are the same abbreviations we used for reals, rationals, and integers, only you put in either a p, an n, a pn, or sorry, an np or an nn. So then escape n reals, or we have reals and rats for the rationals, or npi for the non, and again, that because of how floating cells work, that's kind of hard to see up there, but it says np-ints there for the non-positive integers, and voila. Okay, so these are sort of formatting and sort of elementary things. The next few slides are also sort of elementary math, but it's actually not as trivial functionality as you might think. So common questions that you would get are like, how do I add 5 to both sides of an equation? Or how do I add the respective sides of these equations? So the old answer used to be use thread, or use replace, or map, or something else. The new answer is much simpler, use dedicated functions. So if you want to add 5 to both sides of the equation, say add sides to x equals y5, and voila. Or if you want to add the respective sides, you can give it a couple of equations. And you're not limited to 2 sides. You can have 3 sides as long as you have the same number of sides. Then SubtractSides is analogous. Okay, I'm still okay on time. Only it also has a 1 argument form, which is move everything to the left, well, to the leftmost side. Right, and just for comparison, here are what you used to have to do. So adding a constant was really not too bad, at least if you are comfortable with map or the pattern matcher, although most calculus students are not. And for adding respective equations, again with thread, if you understand it, it's not too bad. But trying to do it with any other way, this was the only other sort of, what would be the map-like way to do it? This was the easiest way I came up with, which is really not very easy. I did have one student who, once he learned about triple at, he tried to use it for everything, including things he really shouldn't have. That's not a very common occurrence. Of course, equations are super simple. What about inequalities? Well, those are handled. Or you can add an equation and inequality, and it'll correctly figure out what the correct inequality to put in. Or if you have inequations, more than 2 sides, it also knows about piecewise. So if you give it a piecewise function, it will, piecewise relation, it'll go in and find the relations and add things. And it also knows about conditional expression, which is very important, as you will see on the next slide. So adding and subtracting is actually pretty simple. Then there's multiplication and division, which at first starts out pretty analogously. You have MultiplySides, and it looks basically just like AddSides. Then you have DivideSides, and it starts out looking okay, but then you divide 2 equations, and you get a piecewise thing out. Or if you do DivideSides on a single equation, you get an equation out. And so we have this option, generate conditions, and it defaults to all, which is a special value for MultiplySides and DivideSides, which means if it needs a condition, it's going to give you all possible results as a piecewise expression. Now, there are various other settings which are specific to, which are general, which are shared with all the other functions we've been recently working on and adding generate conditions to. So for example, generate conditions goes to true means pick one true result, give it to me, and tell me what condition you use to get there. So here it shows the positive side, and voila. With false, it will still figure out a correct answer, but it won't tell you which condition it chose. And then there's none, which means if you need to generate the condition, then don't do anything, just come back as is. Generate conditions goes to automatic, tries to be a little bit clever. So if you need a quote-unquote non-generic result, i.e. something which is true, is a condition, I guess a generic result is easier to define. A generic result is one that's true except at single points, single isolated points. Then don't give those. But if you need a non-generic condition, then give it. Otherwise, so here, so for this condition, automatic and true behave the same way, but for this condition where you just need to exclude b equals 0, then automatic doesn't give the condition, true gives the condition. And since I don't think I have quite enough time, I have some bonus details here on exactly when conditions are generated and the exact relationship between the result and the inputs. If you want to know some if you want to realize just how complicated basic algebra is, it's worth a look. But in the interest of time, I will skip over that. So finally, we have ApplySides, which applies a general function to an equation. So you can exponentiate both sides or take the square root of both sides, and it understands all the same things. The one way it's very, very different is it's really a structural operation. It's not going to verify that what it gives to you is still mathematically equivalent, because that's really, really, really hard / impossible. So for example, here it took the sine of both sides, but that's obviously not this equivalent. Sine of A greater than sine of B is not equivalent to A greater than B. So one example, which I blatantly stole from the documentation, but it's okay because I wrote the documentation, is deriving the quadratic formula using these new functions. So you start out with a quadratic equation. You multiply both sides by 4a. You add b squared minus 4ac to both sides. You factor the left-hand side. You take the positive square root of both sides, which we do by first taking the square root and then applying power expand. Then you subtract b from both sides. And finally, you divide both sides, assuming a is not 0, which is okay because it's a quadratic equation. If a were 0, you would not have started out with a quadratic equation. And voila, x is minus b plus the square root of b squared minus 4ac over 2a. Thank you, Julio. Sorry. Okay, so the last area, and I'll talk briefly about this, is we've been slowly updating the documentation for our functions. Our examples, a lot of them are now inspired by actual textbooks. I mean, we had a group of interns who solved every problem in Stewart using Mathematica. We also looked at Marsden and Tromba for the vector calculus, Colley, so on and so forth. And so these were already introduced sort of a version or two back. If you look at them, then we have sort of pretty pictures explaining what exactly the function is doing. We have tables with different, different ways of entering things. And especially if you look at the application sections, then you have relation to integration. You have rates of change, or with rates of change type problems, L'Hopital's rule. All where did all the areas go? Did I skip relation to integration, multivariate rates of change? I feel like there are examples missing from here. Are we having a build problem? But anyway, lots of examples. Then similarly, limit, which we updated in 11.2 with lots of new functionality. Again, in the interest of time, I'm going to skip over all the many wonderful changes we made, although I will just mention limits are two-sided by default now. That's very useful for calculus students. And again, we have lots of details with different ways of entering things, pictures of what these things mean, and so on and so forth. So that's integrate. Again, in the interest of time, I won't show you, but that's what we've been doing in calculus. And our next point is linear algebra, so I'll let Devendra take over right now.
Hello. Thank you, Itai. I just want to spend a couple of minutes on something I've been thinking quite deeply over the last 1 year. So Itai spoke about algebra, middle school, high school algebra. The next step is linear algebra. And I've been thinking really deeply about this. So the point is that linear algebra, very simply, is a study of linear equations. And today, linear algebra is really the most important requirement you need to fulfill for many things like engineering, data science. Of course, you need calculus, but linear algebra really rules this world of applied mathematics. And when we did a survey last year, we found that linear algebra and differential equations and things like that are really very, very popular courses. So he said, let's try and understand this kind of market of linear algebra, textbooks, etc. Now, when I was a student, we'd study books by Helmholtz and Hoffman and Kunze. So if you could solve Hoffman and Kunze completely, you could pass the PhD prelims. But we were not allowed to ask, what's the application of linear algebra? You just studied it and that was it. I did one book which was by Finkbeiner, and that did a bit more. It had a chapter on linear programming. That was a concession. And you had to hide it because no one would let you do applications, So that's the way life was a long time ago, but things have changed now. And so last year, Roger said, Devendra, buy the top 6 textbooks for linear algebra and study them and pick one. Well, I studied 6 of them, and the 2 finalists were Gilbert Strang's linear algebra and David Ley. Strang, of course, is at MIT, so MIT is a good name to have, and of course, he's a fantastic teacher. But I finally settled on David Ley's book on linear algebra because it had 467 Amazon reviews and wonderful applications, etc. So I then hired 2 interns over the summer. So last summer we finished Stewart, 6,000 examples, and this summer I told them, look, you're going to solve this whole book through the summer. So they sat down 8 hours a day and prepared this solution manual for linear algebra. Every problem in Ley is solved over here, and that's the table of contents. So let me just enlarge it a little bit if I can. And if you click on any one of these, so let's say click over here, application to computer graphics. That's a section of computer graphics with every example typed in, questions answered, everything, nothing left out. And it's quite nice to see how the Wolfram language copes, or doesn't cope in some cases, with what's to be done over here. So that's the letter N. You shear it a little bit, and what happens? It goes there. How do you do that kind of thing? So we now have a complete solution manual for one of the most popular textbooks in linear algebra. And from here on, we'll update the reference pages for linear algebra, inverse, determinant, etc., which are not in, well, compared to the calculus functions, they're not in good shape. And then hopefully next year, we might even have a linear algebra course like the one I did for calculus this year. So I'm gearing up to building linear algebra as a major direction for our team. So tomorrow, Thursday, we have a meetup on linear algebra from 1 to 2, and Itai is organizing that. So if you are a teacher, student, parent, whatever, believe me, linear algebra is important. I'd like to believe that very advanced mathematics is important. No, it's linear algebra that rules in the world. Okay, I wish PDs were more important, but I don't think most people understand them. So the truth is, linear algebra is important. We would like to hear what you have to say. So if you're interested and if you have some time, do come along. It'll be very informal from 1 to 2 in Homewood, and I'll stop over here. Thank you.